Thank you very much. I'm glad to be here. I've sympathized with Google in its struggle against having to be a censor in China. And now today you've given me a nice lunch and given me a chance to talk about my book. So I'm feeling altogether favorable about Google. I should explain the title of this book, Lake Views. It is a collection of essays that I have written, about 25 essays that I have written in the years 2000 to 2008, all of which were written in my home office at a desk by a window overlooking Lake Austin. It's a pretty lake. I have to admit something, if you will keep it confidential, that this isn't actually taken from my office window. In order to get a good view of the water, we had to go down to our boat dock. But it is Lake Austin taken from our property. It's a noisy lake, especially in the summer. You hear the music and the engines of party boats and ski boats going up and down the lake. And so my work as a theoretical physicist is quite abstract and removed from worldly affairs, but sitting at my desk, especially in the summer, I'm continually reminded of the world outside. And as I say in the preface, I sometimes feel like Tennyson's Lady of Shalott, sitting by a window and seeing people going down the river to Camelot. The essays cover a broad range, ranging from abstract scientific issues, which I'm concerned about professionally, to problems of this world, which, as I said, I'm continually reminded of, looking at and listening to what's on the lake. It is a collection of my recent essays. There was published by Harvard Press. There was an earlier collection, Facing Up, also published by Harvard Press, which had essays going up to the year 2000. I try in these essays, where I can, to tell stories that come out of my own experiences, such as they are. For example, in one essay is a review of a book about Robert Oppenheimer, who I knew slightly near the end of his career and near the beginning of mine. My first job as a scientist was as a postdoctoral research associate at Columbia University. And I remember once I was invited to come to the Institute for Advanced Study in Princeton, where Oppenheimer was then director. And I gave a talk to talk about my own recent work. And I gave a talk, and as often happens with young scientists, I emphasized rather abstract mathematics, rather in excess. And Oppenheimer listened to the talk, and at the end he said, "You remind me of myself as a young man." And I said the first stupid thing that came into my head, "Thank you." And he said, "That was not a compliment." In fact, Oppenheimer, and this was the point I was trying to illustrate with the story, Oppenheimer had been rather morose as a young scientist, as a student first at Harvard and then as a postdoctoral research worker at the University of Cambridge. He had even thought of committing suicide. He was so depressed. Only later did he find his métier. And I think he was remembering his own early life. One long article in this book is originally published in the New York Review of Books is about military history. In particular, I tried to make the case that many of the things you read about in military history, things that seem mistaken, are not simple mistakes made by people who were simply had the wrong idea of how to win a battle or win a war, but were motivated by a search for glory, which the military profession is particularly liable to. And I give a number of examples of this. Included among the examples is the overemphasis of the Air Force in World War II in strategic bombing, especially the use of B-17s to play a role in naval warfare, where they were totally unsuited. The tendency of cavalry officers on both sides in the American Civil War to want to stop playing a subordinate role for which they were really very well suited, of providing reconnaissance for the ground force, for the infantry, but instead go off on raids where they could gain glory. And examples like the Confederate General Jeb Stuart and Union General Kilpatrick, Wheeler and the Confederate Army. This seemed to be an institutionalized search for glory on the part of the cavalry, quite removed from any military value their raids would have. Similarly, in the Middle Ages, historians have made a great deal out of the advent of the technique of the cavalry charge with couched lance, that is, a lance held under your arm so that you could deliver the force of the lance at the end. You could deliver the whole force of the horse at the end of the lance. And it was essential to this tactic that the stirrup began to be used in Europe, having been invented in China centuries earlier. I tried to debunk this and said that the use of this tactic was more a search for glory on the part of a military aristocracy than because it had any great military value. And I went through various battles, like the Battle of Hastings, which had been cited by historians as examples of the use of this tactic, and showed that, in fact, it hadn't been used. One of the examples I gave were the tactics of the Royal Navy in World War I in fighting the submarine menace. In 1917, early in 1917, the Germans decided to start a program of unrestricted submarine warfare. And at first, it looked like the Allies were going to lose the war because in the period of 3 months, the German U-boats sank over 800 Allied ships at the loss of only 10 submarines. The Royal Navy was urged by some members of the British government to start a program of convoying merchant ships. And the Royal Navy absolutely refused, because this would be purely defensive. It was not the glorious role that they saw for themselves. What they wanted to do was to go out and hunt submarines in the open ocean. Patrolling was glorious. Convoying ships was merely defensive. It was not a proper role for the Royal Navy. Eventually, they were forced into convoying, and that solved the problem that had been raised by the German unrestricted submarine warfare. Well, in order to illustrate how difficult it is to find submarines in the open ocean when you're patrolling, I told a story about how when I was active in military affairs as a very low-level defense consultant, a member of what's called the Jason group of academics who do defense consulting on the side, I once went on anti-submarine exercises off Key West, which is a nice place to be in the winter. And I was on a destroyer escort, and we also had in our group an airplane and a hunter-killer submarine. And all three were looking for a World War II diesel submarine, which was out there somewhere in the sea off Key West. And we spent the whole day searching for this submarine. And at the end of the day, we found it. And the reason we found it is because they sent up a radio buoy saying, here we are. The idea of patrolling for submarines in the open ocean just doesn't work. And convoying has the advantage that if you're by the ships, that the submarine has to come and attack, and then you find your submarine and you can counterattack. I also had some experience working on missile defense as a defense consultant, and got a very strong idea of how difficult it is to distinguish a enemy reentry vehicle carrying a weapon, a nuclear weapon, coming into the Earth's atmosphere, from how to distinguish that from a decoy, especially when it's above the Earth's atmosphere, where even a balloon, a very light balloon, can provide a credible decoy. And I have an article in here about missile defense that makes the point that not only is an attack by ballistic missiles, which these missile defense systems are supposed to protect us from, the least likely way that any enemy country would ever think of attacking us, because it can't be done anonymously. Our satellites will unerringly determine the country that launched any missiles toward us, so that anything else would be a better way of attacking us from their point of view. But these systems have never been tested in a realistic way. In order to test an anti-missile system in a realistic way, it has to be tested against a reasonable attack with not only incoming warheads, but decoys, which could be balloons or other things. And that's never been done, not in a realistic way. And I don't think it can be done, even with goodwill, wanting to test it realistically, because we'll never know what particular penetration aids an enemy will use against us. So I was very angry. It's not that important whether I'm angry, but I certainly didn't agree with the decision of the Bush administration to tear up the anti-ballistic missile treaty of 1972, which had been brought into being by that great radical Richard Nixon, and instead walk away from any treaty limiting anti-missile systems. I'm glad to see the Obama administration seems to be moving in the opposite direction. There's a good deal in the book about military affairs. In particular, in several articles, I point out that the present concerns that we hear most about, concerns with global warming, concerns with nuclear terrorism, are all serious concerns, and we ought to think about them. But in a way, the people who are worried about them, to the exclusion of everything else, are looking on the bright side, that the most devastating thing you can imagine is a nuclear exchange, perhaps inadvertent, between Russia and the United States. And it's not that impossible. Although certainly relations between Russia and the United States are better than they were at the height of the Cold War, although they're not as good as they were perhaps 10 years ago, the missile systems on both sides are frozen in a Cold War posture, especially on the Russian side, because they have less survivable systems. They don't rely on submarine-based missiles to the same extent that the United States does, which are essentially invulnerable. The Russians' system, as I understand it, is configured so that they can reply to what they see as an American attack within minutes. And they have, at several times, started that process when they thought they were seeing something that looked like an American attack. There was one famous example when we were sending research rockets up into space to study the upper atmosphere from an island off the coast of Norway, and they interpreted that as an attack from an American missile submarine in the Norwegian Sea. And they actually started their countdown toward launching offensive missiles at us. Now, of course, as everyone knows, they didn't go through with it. They stopped it in time. But it's terribly important for the United States and Russia to carve back their missile systems so that instead of thousands or tens of thousands of nuclear weapons, they have at most hundreds, which is more than enough for any reasonable role of deterrence. And again, I hope the Obama administration will follow through on what seem to be their first steps in this direction. There was a Treaty of Moscow signed between the United States and Russia during the Bush administration, which really was more cosmetic than anything else. And there's an article in this book based on testimony I gave before the Senate Committee on Foreign Relations on the Bush nuclear posture program, nuclear posture statement, in which I wring my hands over that treaty, how little good it did in the way of actually cutting back on nuclear weapons. In a way, this is a very old-fashioned issue. I mean, it brings back memories of the Cold War and movies like Dr. Strangelove. But what people don't realize is this is still an important matter. And a nuclear exchange between Russia and the United States is perhaps the one thing that can destroy our country beyond our capability to recover. Well, I should talk a little bit here about science, not just applied science, but real science. I was asked to by the organizers. The first essay in this book was asked for by Time magazine at the turn of the century. They wanted me to make a statement about where fundamental physics was and where we were going. It wasn't hard to do because it hadn't changed very much in the last 20 years. In the previous 20 years, it hasn't changed much since then. The answer is very simple. We have a very good theory called the Standard Model, the work of many hands. I was one of the participants. It's a theory. I think I'm the one who gave it that name. I've never been quite sure about that. It's a theory of particles called quarks, which are inside the particles, inside the atomic nucleus. There are 6 types of quarks. There are particles called leptons, of which the most familiar one is the electron, which makes up the outer parts of atoms and carries electric currents through wires. And then there are other particles that carry forces, like the electromagnetic force and the weak and strong nuclear forces. This theory works. It is not in disagreement with any experiment we can do. And although we can't carry out the calculations for every possible process, in some cases the calculations are just too difficult, we can carry out lots of calculations that can be compared with experiment, and it always works. So it's a perfectly good theory. So why aren't we happy? Well, for one thing, the theory leaves out one of the fundamental forces of nature, the force of gravitation. And that isn't just absent-mindedness. It leaves it out because although we have a perfectly good theory of gravitation, Einstein's general theory of relativity, that's a theory that works only on the macroscopic scale. We can turn that theory into a microscopic theory that works at pretty small distances, the kind of distances that we can probe in high energy accelerators, although it doesn't produce, the theory doesn't predict any effects we can actually observe there. That's our fault, not the theory's fault. But when the theory is pushed to really high energies, really short distances, much higher energy, much shorter distances that can be probed with any accelerator that we can even imagine, the theory loses all predictive value. And we just don't know how to bring the theory of gravitation into the same framework which works so well for the other forces. There's another problem, even apart from the problem with gravitation, and that is that the standard model, as it stands, although it works perfectly well, has an awful lot of arbitrary features that simply have to be adjusted to be what they are to make it agree with the experiment. Not everything, of course, but it leaves you with a dissatisfied sense that there are things we ought to understand that we don't. For example, there are 6 types of quarks. Why 6? Well, we know why it has to be an even number. The theory is only mathematically consistent if it's an even number. But why not 4? That's a nice even number, or 8. We have no idea. There's absolutely no understanding of that. We just put it into the theory. What about the masses of the quarks? The heaviest quark is about 100,000 times heavier than the lightest quark. Where does that ratio come from? We don't have any idea. It's just something it's a number we have to put into the theory to make the theory agree with observation. It's highly dissatisfying. Some people have said, and I argue about this in one of the articles in the book, that science doesn't explain nature, it simply describes it. Well, that isn't the way we feel about what we're doing. We want to explain why things are the way they are. And the standard model gives us a lot of explanatory power, but it leaves us also with a number of outstanding facts that we simply feel we have no explanation for. Now, it may be that the 2 problems are in fact the same problem. That is, that when we carry our theories, when we develop a theory of gravitation which works at all energies, and right now string theory seems the best candidate for that, although progress has been disappointing, that we will find that that theory is only mathematically consistent if there are precisely 6 quarks with precisely the masses we are putting into the theory to make the theory agree with observation. That would be wonderful. Even if we can't do experiments at those enormously high energies or enormously small distances at which the quantum theory of gravitation begins to be important, if the theory, because of its mathematical consistency, requires the unexplained features of the standard model to be what they are, then we will feel that theory is completely successful. String theory is our best chance for that. I did work in string theory ages ago, but I haven't worked in it for some time. One of the reasons I haven't worked in string theory is because an entirely different area, or apparently different area of science has become tremendously exciting, and I refer to cosmology. Cosmology is the study of, as you know, of the structure and evolution of the whole universe. And when we study the very early universe, it raises these questions of fundamental physics in a way that we can't raise them in our laboratories. One of the most exciting developments in cosmology, which is the subject of one of the articles here that was written, the Times Higher Education Supplement in London had an issue devoted to a celebration of the 100th anniversary of the Nobel Prize. And they asked various people to contribute to it, and many of them contributed articles about international problems, and I decided I would describe this problem, which at that time was very much on my mind. Dark energy is an energy inhering in space itself. It is not an energy in the masses of particles as described by Einstein's E equals mc squared. It is an energy, a certain number of calories per quart of space, or whatever units you want to use for energy and volume, that's there irrespective of what's in the space. And the mystery is not why is there such a thing as dark energy, why should empty space have an energy. That's been known for a long time. Theoretical physicists for decades have been trying to calculate the value of this, and the problem is that the value always came out too large. We can calculate, because we really can't calculate it. What we can do is calculate the energy in empty space due to quantum fluctuations that have a wavelength no smaller than a certain amount, the smallest distance that we have probed in our laboratories, roughly 1/100th the size of an atomic nucleus. But if we calculate the amount of energy in space due to fluctuating fields like the electromagnetic field and the gravitational field, including all wavelengths down to the shortest wavelength that we think we really understand, we get an energy which is too large. Well, I'm tempted to say, since I'm here at Google, too large by a factor of about a Google. That is a 1 with 100 zeros. Is that what a Google is? Yeah. Yes, okay, good. That's about the error in our calculation. I've referred to that as the worst failure of an order of magnitude estimate in the history of science. Now, it's not a paradox. When I say it's too large, what I mean is if it was that large, it would wreck the universe. This energy, although it doesn't have much effect, since space is very large, it produces a gravitational field which affects the way the universe expands. And from observations of the way the universe is expanding, astronomers throughout the 20th century have been able to put fairly stringent limits on this energy. It was always consistent with zero, and most people thought it was zero, but it certainly was not as large as the theoretical physicists were calculating, by a factor of about a Google. Well, many of us worried about this. It's not a paradox because, as I started to say before, because there were other things we couldn't calculate, like the effect of fluctuations at even shorter distances, and maybe they all cancel. But that cancellation would have to be good to 100 decimal places, which is not exactly a paradox, but it leaves you with a feeling there's something you haven't understood. I made a proposal in 1987 of what the solution of this might be. I proposed that the energy in empty space may be an environmental parameter. That is, the universe, as appeared in many theories, in particular a theory of cosmology called chaotic inflation due to Andre Linde of Stanford, the universe may consist of many parts, and the constants, what we call the constants of nature, may vary from one part to another. Our Big Bang may be just one episode in a much larger cosmos. We sometimes call it the multiverse. And we would naturally only exist, well, any astronomers who ask questions about the dark energy could only be living in parts of the multiverse where the dark energy was small enough so that the universe evolution would last long enough for them to have evolved, which in fact I showed meant that the dark energy couldn't be much larger than the mass density in ordinary space that we know about, the stars, the intergalactic material. The dark energy could be a few times larger than that without interfering with anything, but if it was, say, 1,000 times larger, then it would have dominated the universe at the time galaxies were forming, and they wouldn't have formed. It just would have been impossible for matter to clump together and form galaxies, and then there wouldn't be any stars or planets or us. And it's very much like the argument of why water is liquid on the surface of the Earth. If the Earth were the only planet in the universe, that would really be amazing, that the Earth was just the right distance from the sun so that the temperature was right for water to be liquid. But we now know that even in our own galaxy there are billions of planets, and it's natural that occasionally one of them is in the right position for water to be liquid so that life can arise. We think that's probably necessary for life to arise. And so there's no miracle about the fact that living creatures like us live on a planet which is in that comfort zone. And the same reasoning would apply to the multiverse. Then, and I did a calculation with two colleagues at Texas, Martel and Shapiro, and we actually worked out what we thought would be the most likely value of the dark energy on this basis. And then in the same year that we did that calculation, 1998, the dark energy was discovered by two groups of astronomers working with the Hubble Space Telescope and also with ground-based telescopes, studying the way that galaxies are moving at great distances away from us, how their velocity depends on how far away they are. They were able to conclude that the expansion of the universe, which had always been thought to be slowing down because gravity was pulling everything back together again, in fact is speeding up, an effect which is just precisely the sort of thing you would expect from a cosmic expansion which is driven by dark energy. How much time do I have? Well, I'm almost out of time. Well, I'll end pretty quickly. This idea of the multiverse was the topic of a conference at Trinity College, Cambridge, at which I spoke. And on the way to the conference, I tell this story in the book, in the Austin airport, I picked up a copy of a magazine called Astronomy. And the magazine described an earlier conference at Stanford in which various people had given their feeling of certainty about the existence of a multiverse. Multiverse meaning many big bangs, ours just one little part of a much larger universe. And it quoted André Linde, who, as I said, was the originator of this idea of chaotic inflation, which leads to a multiverse picture, as saying he would bet his life on the existence of the multiverse. And it also quoted Martin Rees, also known as Lord Rees, who was the master of Trinity College and was our host at this conference I was going to, saying, well, he would bet his dog's life on it. And in the conference, I thought it was incumbent on me to give my own impression of how certain I was about the multiverse, and I decided I would top them. I said that I would gladly bet both the life of André Linde and Martin Rees's dog. One of the topics that I write about in a few places in this book, two articles, is religion. I reviewed a book by Richard Dawkins for the Times Literary Supplement in London, and I thought he had gotten some unfair criticism. I gave it a generally favorable review since I tend to agree with him about religion. I thought he'd gotten some unfavorable reviews, in particular one in the London Review of Books, I think it was, that criticized him because he's not an expert in theology. And I thought this was kind of unfair because, you know, theology is a science about something that doesn't really exist. And I didn't see what the value of expertise in theology was. I said it was a little bit like someone who wrote about astrology in a dismissive, negative way, and then was criticized by a reviewer saying that this was someone who was dismissing astrology and didn't even know how to cast a horoscope. One place in which I disagreed with Dawkins was, like many Europeans, it seemed to me he had a vision of America as a place that was rife with Bible-thumping fundamentalists. Well, there's some truth to that, but I find that it's greatly exaggerated. And in fact, when I talk to people, even once a Catholic priest, and I describe this in the book, I find they don't have, even though they believe in religion, they really, in fact, get angry if you criticize religion when you ask what they actually believe about supernatural beings or about the afterlife or about original sin. They're likely to say, well, it isn't really that important what you believe. The important thing is how you live. Well, I couldn't agree more with that sentiment, but it shows that there's a weakening of actual belief as opposed to observance or affiliation in America. Another example I give is, as you know, I live in Texas, and that's supposed to be a rather religious area. And indeed, many of my friends are serious about identifying themselves as religious. In many cases, their religion teaches that a disbeliever like me is doomed to hell. And yet, I've observed that after 30 years in Texas, no one tries to convert me. Now, there are two theories that explain this. One theory is that my friends really don't mind if I spend eternity in hell. The other theory is that they're not that sure about what they actually believe. And naturally, I prefer to follow the second theory. The last article in the book, which will also be the last one I talk about today, except for what you ask about in the Q&A, is a talk I gave as the Phi Beta Kappa oration at Harvard in 2008. These Phi Beta Kappa orations are a great tradition. They go back to the 18th century. There was a famous one given by Ralph Waldo Emerson called The American Scholar, and in my talk I refer to it frequently. The title is Without God, and because in it I said, I really don't want to be in the position of being a missionary trying to convince people they shouldn't be religious. In a career of having written about things like missile defense, and I'm also against the manned spaceflight program. I think it's a waste of money. In writing about religion, of course. I think I've kept a perfect record of never having changed anyone's mind. And so I'm not here at Harvard as a missionary, but I did want to talk about the prospect of life without God. What kind of life can you have without God? And I don't think it's a trivial question. I don't think the answer is that science provides everything you need, because science actually presents a rather chilling worldview. It's not only the obvious thing that we're here on a planet which is only one of 8 planets in our solar system, and that our solar system is only one of millions and billions of solar systems in our galaxy and so on. And this Big Bang that we're in may only be part of a much larger multiverse, as I said. It's not just that. It's that the things that we most prize, that we regard as most precious, our love for our families, our spouses, our children, we can understand as the result of evolution having produced these instincts after millions of years of random mutations which are then selected in a Darwinian way. I find it quite a chilling picture. We don't find in science any guide to what we should value. It just doesn't provide any help for that. It faces us with a strong sense that when we die, there's going to be nothing afterwards. And we have to somehow or other live on a knife edge between, on one hand, a sort of foolish optimism, wishful thinking, which is the way I characterize most religious belief, and on the other hand, a simple despair. And one thing that helps us a great deal is having a sense of humor. Just as we laugh with sympathy and without scorn when we see a one-year-old trying to take her first steps without falling down, we can be amused by ourselves trying to live on a knife edge between us again. But we can still take some pleasure, or maybe just a sort of grim satisfaction, out of the fact that we can live on this knife edge with good humor, without despair, and without God. Thank you. Not too bad. Well, I'm open to questions. I'm sure everyone agrees with everything I've said, but maybe you can think of something to ask.
Do you guys have the Dory question?
Page, but I don't know if everybody's seen it.
It's in the process of coming up. The computer downloaded some updates and restarted.
Oh no.
Well, I don't understand any of that, so. Please, someone raise their hand. Yes, thank you.
So I was first going to ask you, in the multiverse concept, if you think that different universes that could exist are simultaneous or sequential. But then it occurs to me, does the concept of time even necessarily...
No, that's the problem. The problem is that, at least in this chaotic inflation picture, each bubble of expanding stuff has its own time. And there really isn't any definition of time that works across the multiverse. And in fact, that's one of the great problems in thinking about it, because even theoretical physicists who are used to thinking about things rather far removed from everyday experience are sort of addicted to the idea of thinking in terms of an ordinary time which advances 1 second after another. And your question is right on the money. It focuses on one of the real difficulties. But there are less demanding or less abstract kinds of multiverse theories. Some theorists have considered a multiverse which is just one universe but which goes through a series of stages, where it's very easy to think about that. It's like a ball rolling down a hill that's corrugated, and it goes and it's in a little valley, and then it goes into the next valley, and in each valley you have something like a Big Bang, but it's different from one to the next. This is an old idea that goes back, I think, to the 70s. Then there's another picture of the multiverse that's even more abstract and harder to get your head around, but in a way seems to be almost inevitable, and that is that the different parts of the multiverse are not different episodes in time or different parts of space, but different terms in the wave function of the universe. That is, just like everything else, quantum mechanics applies to the whole shebang, and the wave function of the universe is not something which describes just a single Big Bang, but has many terms in it which describe different possibilities, just like in the famous example of a wave function which has terms corresponding to Schrodinger's cat being alive and other terms that correspond to his cat being dead. And at least according to the one interpretation of quantum mechanics, which is right now probably the most popular, the Everett many worlds interpretation, that's inevitable. I don't know if that's going to remain the standard view of quantum mechanics, but it's hard to avoid that. But it's very hard also to think about it, because there isn't even any discreteness to it. I mean, it's just a continuous variation. One of the things that has encourage belief in the multiverse are developments that have nothing to do with cosmology in themselves. I mean, don't arise out of people thinking about why the dark energy is small or anything like that. It's developments within string theory. String theory is a theory. We're not too sure exactly what the theory is. I mean, that's one of the problems. But as far as we understand what it is, there is one string theory, but it has many solutions, each one of which correspond to a particular kind of universe. The number of solutions is something like, well, it's been estimated to be of the order of 10 to the 500. In other words, a Google to the 5th power. I can't help using that word here. And a very large number of solutions. And there are questions, do these correspond to different actually existing sub-universe parts of a multiverse, or are they just mathematical possibilities? We don't know the answer to that. And in fact, it would help a lot if we knew what string theory was. Another question? Oh, what is this? Rumor has it that when UT hired you from Harvard, there was a stipulation they would pay you $1 more than the football coach. Any truth to this story? Easy question, no. But in any case, I want to point out that whatever the football coach has is being paid. I have tenure and he doesn't. My astrophysicist friend wants to know your thoughts about inflation, the cosmological kind. What caused it, whether it's the same as dark energy, and what measurement will give us the most diagnostic information about it, the smoking gun? Well, the last part of that is really worth talking about. I already answered the first part. We don't know, of course, what caused it in the sense of an ultimate cause. We can trace the history of the Big Bang back to a time before the universe filled up with matter and radiation, to a time of so-called inflation, when the expansion of the universe was being driven by a dark energy, but a dark energy vastly more than the dark energy that we detected in the present universe. What went before that, we don't know. The chaotic inflation of theory of Lindy suggests that there was no initial moment, that what we have is almost like a steady state theory, but in a grand sense. That is, it's something like a boiling kettle of tea, that you have bubbles being created at random again and again, each one of which then becomes a Big Bang. But this has been going on forever. The one Catholic prelate, the Cardinal Archbishop of Vienna, Christoph Schönbrunn, and I quote him in the book, attacked the multiverse idea because I think, he didn't particularly say what he didn't like about it, but he thought it was hostile to religion. And I guess it is, because it takes away it can, at least in one version, take away the idea of a real beginning. But that it wasn't developed as Schönbrunn said it was. He was wrong. It was not developed for that purpose. It came out of purely scientific issues. What measurement will give us the most diagnostic information about inflation? Well, that's really interesting. There are experiments which are underway that study tiny fluctuations in the cosmic microwave radiation background, a kind of radiostatic that fills the universe. This radiostatic was not itself emitted very early. The universe was already 380,000 years old at the time when this radiation was emitted. The universe at that moment suddenly became transparent to radiation, so we can see what was present at that time. But it has an imprint in the form of sound waves, which are greatly expanded versions of quantum fluctuations that occurred during inflation. And there has been great work. This is one of the most exciting developments in science in the last decade, studying in detail these tiny fluctuations in the temperature of the microwave background, things like a variation in temperature of 1 part in 100,000 as you go from one point in the sky to another point a degree away. That's sort of typical numbers. By studying these fluctuations, studying the correlations between the temperature in one direction and the temperature in another direction, you really get a handle on what was going on during inflation. Because those quantum mechanical fluctuations then have grown up to be the fluctuations that we see in the microwave background, which have then grown up since then in the ensuing 10 or actually 13.7 billion years to become the galaxies that we see in the sky. And the study of this cosmic microwave background radiation is an exquisite tool for learning about inflation. It is hoped that they may be able, with new satellites like the Planck satellite, which was recently launched by the European Space Agency, to detect effects of gravitational waves emitted during inflation, which then imprint themselves on the sound waves that affect the temperature of the microwave background radiation when the universe was much older, 380,000 years older. It's a tough thing to do. I'm really glad that the Europeans are doing things like this, launching this kind of satellite, and I wish NASA would do more of it. It has done a wonderful job with the previous satellite, the Wilkinson microwave anisotropy probe. And the reason I'm hostile to the whole manned spaceflight program is it draws funds away from this. When President Bush announced his new vision for going to the moon and Mars, almost the next day, the NASA Office of Space Science announced a cutback in programs like this kind of thing, real science, because it didn't adequately support the president's vision for NASA. Well, again, I'm glad that President Obama's administration is reversing that.
The very first question is on top.
What? Oh, what do you most look forward to seeing the Large Hadron Collider provide evidence about? Well, the Large Hadron Collider will probably discover the so-called Higgs boson. That's expected in the Standard Model. That's the one missing part of the Standard Model that hasn't been discovered. It's not surprising it hasn't been discovered. It interacts very weakly, and you wouldn't have expected to see it in earlier experiments. We will expect to see it at the Large Hadron Collider. But if that's all they see, we're in trouble, because that discovery alone will not give us much insight about what to do next. The most exciting thing that would come out of the Large Hadron Collider would be the discovery of a symmetry that physicists have been talking about since the 1970s without a grain of it. Well, there is a grain, but not much more than a grain of experimental support. A symmetry called supersymmetry, which says that there are families of particles which in a way are orthogonal to the families that we already know about. We know, for example, the electron and neutrino form a family, they're siblings. But according to the supersymmetry theory, they have partners which have, the electron and neutrino are spinning. They have partners which don't have spin, called the selectron and the sneutrino. There's a whole slanguage about this. That are predicted by supersymmetry. You might say, where did this idea come from? It really came from the fact that if you try to go beyond the family structure that we know about in the Standard Model and think of some other family structure that would connect particles of different spin, there is only essentially one way of doing it. And the fact that there's only one possibility mathematically focused attention on this, and a tremendous amount of work has gone on. I wrote a book about supersymmetry. Many other people have done that. Finding signs of supersymmetry, finding certain particles that are predicted called gluinos or binos, would be evidence of supersymmetry, and that would really give us the kick in the pants we need. Perhaps the most exciting thing would be if one of these particles turned out to be the particle that makes up the mysterious dark matter, which we know about is in space. Now, this is different from dark energy. Dark energy is an energy that inheres in space itself. It has nothing to do with particles. Dark matter is just particles, more particles, kind we haven't seen before. They're dark, they don't interact with radiation. We know about them because of their gravitational fields. It's not only their effect on the expansion of the universe, although they have an effect, but they affect the dynamics of galaxies, how they rotate, and they affect the dynamics of galaxies within clusters, how they move within the cluster. And we can even see effects of the dark matter because the gravitational field it produces bends light, and as a result it shifts the images of galaxies that are along the same line of sight as clouds of dark matter in a way that we can detect. So there's lots of evidence for dark matter. It makes up about 5/6 of the matter of the universe. In fact, maybe I should say the energy budget of the universe is about 73% dark energy, about 23% dark matter, and the rest of it, maybe 4%, is ordinary stuff. Atoms, intergalactic material, stars, galaxies, planets, you and me. All of us, and everything you can actually see when you look at the sky, is just a contamination in a universe that is overwhelmingly dark matter and even more dark energy. And finding dark, the thing is, we don't have a theory about what, rather we have several theories about what dark matter is. And the theories allow us to calculate how much dark matter there would be left over from the Big Bang once we discover the properties of the dark matter particles. If the dark matter particles are created at CERN, our theories are good enough so that we'll be able to work out how much of them would be left over from the Big Bang and answer the question, is this really the dark matter we've been observing astronomically? So I don't think there's anything more exciting that can possibly come out of the Large Hadron Collider than to discover the material out of which makes up most of the matter of the universe. Are there more questions here? Oh.
Want to advance the...
Well, the second one is highlighted.
I'm sorry.
Well, that one I think you covered.
Yes, sir.
I'll ask a question, just kind of a follow-up to what you just said then. So on a percentage basis, it sounds like the score is physics 4 and the universe 96. Does it worry you that we're going the wrong direction, or what do you think?
No, it's surprising and it's moderately disturbing, but I don't think we're going in the wrong direction. Dark matter is not a fundamental challenge. I mean, we don't know what it is. We can think of a number of alternatives. None of them require a really fundamental re-understanding of nature. For example, there's a particle called the axion, that the necessity for which was independently pointed out in, God, how long ago was it? I think 1976 by Frank Wilczek and myself, based on earlier work by Pache and Quinn. And the axion may be the dark matter. Well, we've known about axions for a long time. We don't know precisely what their properties are because there's one unknown parameter that we don't know in the theory of axions. If that parameter has a certain value, then axions are the dark matter, but we simply don't know what. Finding the dark matter will certainly settle a lot of issues, and it's awfully important, but it won't show that we've been looking the wrong way conceptually. The dark energy is a different thing. People have been trying for decades to find any theory, even if it isn't supported by experiment, that makes a prediction for dark energy that isn't inconsistent with observation. The only theory that really does that is this multiverse picture, and that's an incredible expansion. In fact, in a way, it's a very disappointing development in science, because it means that a lot of the things that we had hoped to calculate from first principles, we never will be able to, because they're just accidents of our environment. But that's happened before in science. You know, there was a time when Kepler developed a theory that predicted the ratios of the sizes of the planetary orbits. It was based on a geometrical construction with imagining that the planets rode on spheres that had inscribed and circumscribed platonic solids. It was very complicated. He did it as a young man. He learned better later. But that was a natural thing to do when it was thought that the planetary orbits were part of a fundamental description of nature. When Newton's work came along, it was rather disappointing. It had nothing to say about that. The size of the planetary orbits was simply something you had to take from observation. And we know now, at least we think we do, that it's just an accident of history, that the way the solar system was formed, you have Mercury, Venus, the Earth, and so on, and there were certain planetary orbits. We'll never know why the Earth is precisely 93 million miles from the sun. It's just something we've given up worrying about. It's a historical accident. So it may be that some of the things that we worry about in science, why is the charge of the electron what it is? Why is the dark energy what it is? Why is one quark 100,000 times heavier than another? It may be that some of them are just historical accidents. And that would be very disappointing. And there are some physicists who hate the idea. David Gross, a very distinguished physicist who heads the Institute for Theoretical Physics at Santa Barbara, said, "I hate this." Oh, I quote him saying that. And I can understand why, but you know, that's one of the great things that we do in the history of science. The history of science is not just a history of solving problems or answering questions. It's a history also of discovering what questions are the ones to ask. Kepler was wrong in thinking that the question of the sizes of the planetary orbits is one that a theorist should consider. I mean, this isn't something we can say anything about. It's a historical accident. In the same way, we may discover other things that we have always wanted to calculate, we never will calculate because they're historical accidents. But as always, the hope is there's enough that you can calculate so that your theories are confirmed and you know you're in the right direction. We know that the standard model is right because it has made so many predictions which work so well. It couldn't be a mistake. It's not the final answer. It's part of the final answer. But we know we haven't been going in the wrong direction in developing the standard model. Just as Newton was not going in the wrong direction when he developed his theory. It's only part of the answer. It's only an approximation to a more exact theory. But it's a good approximation. And in fact, it's arbitrarily good if you consider systems sufficiently large and slowly moving. That's the way it works. We don't really go back. In the history of science, in the last, over a century, well, let's say the history of physics, we've made no mistakes in the sense that a widely accepted theory was turned out to be simply wrong. We've discovered that some of our theories are not as exact as we thought they were. Some of them are true for reasons that were different from the reasons that the inventors had in mind. I mean, that's happened to the general theory of relativity. Most people now do not look at it the way Einstein looked at it. But it's not a mistake. And I don't think our current theories are mistakes. But they are certainly incomplete. And that's what we're hoping will, eventually will stop being true, but will become less true, we hope, with the developments that we find at the Large Hadron Collider. Yes?
Could you elaborate a little bit more on how people view Einstein's theory differently than he did?
Yes. Einstein developed general relativity as a fundamental theory of gravitation. And he put tremendous emphasis on the geometrical picture. He thought it was gravitation in terms of curved space-time. Well, we do too. It's a useful metaphor, although we don't think that's what's fundamentally at stake. Many of us think that general relativity is simply the inevitable theory of a particle of mass zero with a certain spin, a spin twice the spin of the particle of light, the photon. And that if you imagine a particle of mass zero and spin twice the spin of the photon, then mathematically it will be general relativity, with one caveat. Einstein thought that his theory should be mathematically as simple as possible. And to be a little technical, that meant he only considered a theory where the field equations would be second-order partial differential equations. In other words, for people listening who, I know everyone here knows what that means, but for people who may hear this who don't know what it means that the equations involve fields, and they involve the rates of change of fields, and they involve the rates of change of the rates of change of fields, but not the rates of change of the rates of change of the rates of change of fields. Now, Einstein did this because he thought he was working on a fundamental theory, something embedded at the deepest level in nature, which he thought had to be as simple as possible. Today, we don't think that that assumption is correct. We think that Einstein's general relativity is just the first term in what's known in the trade as an effective field theory, in which all the higher terms, which Einstein would not allow in his field equations, are actually present. But they're present with coefficients which involve a fundamental length called the Planck length, which is so short that any experiment we do in astronomy, or even in atomic or nuclear physics, will inevitably agree to a very high degree of accuracy with Einstein's theory. It's only when you get to the early universe, where everything is cramped together in scales comparable to the Planck length, that the higher corrections become important. And in fact, that's what I've been working on, as a number of other theorists have been working on, how to use not Einstein's theory, but a more realistic theory, which includes these higher terms, in dealing with a problem where they become important. The only other place that they become important is in the collapse, in gravitational collapse, as in a black hole. But we don't have any observational handle on what goes on within a black hole. We actually can see much better into the early universe than we can see into the heart of a black hole. So and cosmology has been so exciting lately that we've been pushing this study of the successor theory to general relativity, the effective quantum field theory of gravitation, into the realm of the theory of inflation. There was a hand here? No? Yes?
Do you think quantum computing will ever become practical?
I have no idea. One of my best graduate students, John Preskill, left particle physics after he got his PhD and became an expert in quantum computing. And I would have to ask him. I don't know. I mean, in a way, I hope not, for a philosophical reason, which has nothing to do with computing. Quantum computing depends on this weird feature of quantum mechanics called entanglement. That is that you can have a situation where things that are at a macroscopic distance, not just at atomic scales, but ordinary scales, are described by a wave function which has the counterintuitive properties of quantum mechanics. For example, it isn't a state where you have one spin up and another spin down, but a mixture of states where both possibilities, up, down, and down, up, are realized. So that if you make a measurement at one part of the laboratory, you immediately know something about what's happening very far away in the laboratory. This weird property of quantum entanglement is difficult to study because it can be wiped out by almost any environmental perturbation. But if you take quantum mechanics literally, if you eliminate all environmental perturbations, it's exact, and these predictions are true, and they've always been verified observationally. I hope, and a lot of theorists hope, that eventually it will be discovered that quantum entanglement destroys itself. So that, because that would solve these profound questions about quantum mechanics. It would mean that no, Schrödinger's cat cannot be alive and dead at the same time. The nature of quantum mechanics is such that the wave function decays into a wave function in which Schrödinger's cat is either alive or is dead. We would not have parallel universes, one universe in which Schrödinger's cat is alive and the other in which it's dead, which would mean that there would be a fundamental physical limitation on quantum computing. I hope that's true, but it's only not because I'm against quantum computing, but because I'm dissatisfied with our present understanding of quantum mechanics. That would also have grave implications for the multiverse idea. There's some very interesting work on theories in which the wave function decays into something that's understandable in ordinary macroscopic terms. The paper by, I'm afraid I'll forget one of the authors, Girardi, Rimini, and Weber, who explored this. And I'd like to learn more about it and think about it myself, but cosmology is so exciting now that I haven't had a chance. Well, thank you all. This has been a very gratifying audience to talk to. I mean, from your questions, I can see that you've thought about these things. And, well, I hope those of you who do me the honor of buying the book will enjoy it. Thank you.